let's start. So yeah, we will talk about this book on digital signal theories. That yeah, we just talk about this book as a bunch of like resources on math and the programming use Python. That yeah, I guess I like Charles and I are similar. We both prefer system languages, but well, Python is definitely improvement over MATLAB in my opinion, and a lot of people in this space use MATLAB, but Python is gaining popularity.
I
And
think a lot in the machine learning stuff, there's some application for this as well. So that's probably why a lot of Python interest.
yeah,
That maybe part of why.
yeah, like the current AI stuff is definitely one reason why Python gets so popular, and also a bunch of further reading stuff, acknowledgement. Okay, let's jump into it. So the first chapter will just talk about signals as a mathematical object. So just an introduction to signals. Preliminary talks about what is a signal. It does not cover mathematical fundamentals because the more advanced concept will only be used later. Sometimes use the term basic when describing certain ideas. By this I mean that these ideas are the base level upon which we build. This is not the same thing as being easy. Why writing this when they can just change the terminology like fundamental or something? Yeah, but I fully agree. A lot of like so-called basics math people learn in high school or early college, it's not easy. Just like further things build upon them. Yeah, yeah. Anyway, so at a high level, a signal is a way to convey information. There unfortunately isn't a simple, concise technical definition of signal that provides us with much insight. The most intuitive example of signal, at least for acoustically inclined people, is the voltage on a wire connected to a microphone. And we can say something like this. And we can denote this curve with notation like this. So I don't know if my understanding is correct or not, but at least from my personal understanding, a signal is basically a function that takes the input and gives an output.
I think that's a safe understanding. Yeah.
Yeah, and I think my understanding is something like a system or a filter is basically a higher order function that takes a signal and returns a signal.
Yeah, in the discrete case, it takes some number of samples.
Yeah. So
Like, cause yeah, they're
yeah,
just
graphics are
saying it's like
signals. Yeah. Our signals are usually a function that takes position and time and return. Yeah, exactly. So our signal are often both in time domain and in the called space domain. Yeah, at the same time, or sometimes it's separate. But yeah. But the simplest case is just in the one-dimensional time domain a signal. Yeah, and there are other kind of signals which we just talk about, like an image is like in a space domain over two input coordinates, and measure the brightness at this point. And most technique we developed can be carrying more general type of signals. So we will focus on the time domain. Notations, we use the function call notation parentheses to denote a continuous time signal where t can be any real number. We read it as signal x at time t, and we use the bracket notation to denote a discrete time signal where n must be an integer. We read this as an n sample of the signal x. For the first chapter, we only deal with continuous signal, and discrete signals will be introduced in the next chapter. But it's important to keep clear the distinction in notation: parentheses for continuous and the square brackets for the discrete sample indices. And when the usage is clear, we may omit the time or sample index and refer to signal just by the name, which refer to the entire signal. Because we often use letter X to refer to signals, we will need a different symbol to represent multiplication. So we use dot for this. Oh, interesting. Is this the reason why, like, more upper level math start to use less this symbol? I guess it makes sense. Like, people when start to use dot rather than multiplication is in middle school, where we start to introduce like algebra with like symbols such as x. Yeah, that
I
makes
think in
sense.
some contexts, yeah, things like asterisks start becoming overloaded notation as well.
Yeah, they talk about, because asterisk often means convolution, right? But yeah, dots usually just means multiplication, unless you have a vector or something. But otherwise, for number, it's just multiplication.
Right, and even with dot product, it is still kind of just a multiplication, so that does transfer well.
Yeah, I guess for the vector and matrices, it's more complicated because you can have multiple kind of multiplication. So you have specific meaning for dot, but for number, it's pretty straightforward. And yeah, the asterisk, unlike in programming languages, in math notation, it often means convolution. Sometimes it also means XOR, but anyway, so we use the dot for multiplication. And yeah, we will use xt to represent an arbitrary signal. If we need to refer to a specific signal, it will be defined by mathematical formulas such as this. We define a pure tone oscillating at 1 cycle per second. Yeah. most of the time we do in signal processing and then modifying signal in some way. For example, applying a low pass filter to remove high frequency content. Yeah, we can think of this as applying some function to the input signal and produce output signal y, if we write as this. I guess this is the like kind of the definition of a system, but I guess this book does not introduce that concept. So yeah. So conventions. Yeah, we use xt and yt to refer to input and output signals. Time will be referred to as letter t. It will be measured in unit of seconds. Time should be understood to be continuous valued and starting from 0. Discrete quantities will be referred to by the letters n, m, or k. Also start from 0. Measure a sequence of lengths n, have indices from 0. So we will have a default assume that signals are 0 valued when t for n are negative. So I think this also have a name. It's called causal signals. But this is a causal system that's kind of different, but at least I think causal signal is the name. Okay, some people define, okay. Yeah, anyway, this is this book's assumption. So we will always deal with this kind of signals, which will simplify some kind of math. Angles will be denoted by Greek letters theta or phi, and measured in unit of radians because degree sucks. So
Dear
radians. I remember like dear in GUI has that one function that some parameter take degree and some other parameter take radians. It's so confusing, I remember. Yeah, anyway.
You keep a lot more numerical precision for the smaller numbers with radians. That's one benefit.
Yeah. Use letter J to refer to imaginary unit. So that's because for electrical engineers, I is usually for current, so they use a different notation. And interestingly, for some reason, Python also decided to use J to denote imaginary units. I don't know, is it because like some people from scientific computation background influence this deletion, so they also use J. So complex numbers will be denoted by letters Z and occasionally W. In general, X and Y can be assumed to be real valued and Z can be assumed to be complex valued unless otherwise stated. Okay. And we will occasionally see Python like this. Okay. So nothing too interesting so far. 1.2 is about periodic functions and waves. So a signal is said to be periodic if there exists some finite t0 greater than 0 such that for every time t, like xt plus t0 is equal to xt. Like this why is it like signal is a function? Like this is exactly same definition of like periodic functions, and here is just periodic signals. Anyway, so the smallest such t satisfying this equation, if it exists, is called the fundamental period. Sometimes we just call it the period, but anyway, like multiple of t0 can also be a period. Or in some cases, like if it's a constant function, then there's such t0, like there will be no smallest t0 exist at all. So yeah. The different signal may have different periods, and some signals may have no periods at all. Yeah, period is the shortest amount of time it takes. And here's an example, like a pulse train is a specific kind of signal that will be one at like regular intervals and 0 on all the other locations. And yeah, we can see it's periodic because yeah, just this graph illustrated. Yeah, the signal above is periodic. Note that this must hold for every time t, not just the location of the pulses. Yeah, so if we add some random stuff in the middle, then it's no longer periodic. And yeah, if the signal is periodic, it must repeat forever like this. If a signal does not have a periodic, we call it aperiodic, and we assign a period to be infinity. Think of this as means you need to wait forever before seeing a signal repeat itself. So aperiodic signal come in all kind of flavors, like random noise is aperiodic. Yeah, if it isn't, it's probably not a noise. And also, aperiodic signals are not random or unpredictable, and not necessarily, we should say. Like monotonically increasing sequence is like perfectly predictable, but still aperiodic. Yeah, and the final example, the staircase signal is also aperiodic. Yeah, most signals are aperiodic, but we typically use periodicity as a conceptual tool to understand idealized signals. Helpful to remember, any signal of finite duration can be made periodic by playing it in a loop. Yeah, the idea will come back later when we get to Fourier transform. Yeah, like Fourier series only work for periodic signals, but for aperiodic signals we still have a way to deal with them with like Fourier transform. fundamental frequency. The period are defined in unit time. How long must we wait before observing the signal repeating itself? But often it is more convenient to think in terms of how many times a signal repeats itself within a fixed duration of time, typically 1 second. So this idea provides a definition for frequency. How many cycles does a signal complete in 1 second? Frequency is measured in the unit of hertz, where 1 hertz denotes 1 full cycle in 1 second. And also the fundamental frequency is just inverse of fundamental period. Yeah, frequency need not to be a whole number. And period also don't need to be a whole number either. Yeah, frequency is 2/3 hertz for the above example. If the signal are aperiodic, then the fundamental frequency is defined to be 0, which means it completes 0 cycles in 1 second, or any number of seconds. Yeah, this definition is primarily used for notational consistency. If a signal is aperiodic, it's also common to say there are no fundamental frequency at all. So why T0 and TF? A lot of other sources still don't have those subscripts at all, but they use them for those fundamental values. So the purpose is to distinguish fundamental period and frequency from arbitrary time or frequency, and to highlight the connection between fundamental and harmonics and overtones, which are often denoted as F1, F2, etc. So the second point is definitely not arbitrary. However, it's important to keep in mind that any periodic signal will have a fundamental frequency. We typically only discuss harmonic in the context of sinusoids. Does it? Because I immediately think about constant function. Is constant function like completely satisfy this definition, but it does not have a fundamental period or fundamental frequency? I don't know.
And yeah, I think that might be an edge case.
Yeah. Okay. What is a wave? So there are many kinds of periodic signal: pulse trains, square waves, triangle waves, sawtooth waves. But among all periodic signals, sinusoids are in many ways, and most important, and mathematically well behaved. The term wave is therefore often used synonymously with more specific sinusoid. Okay, but it's more common. I guess we also call those things waves. So I guess it's also common to just call all those periodic functions waves. But yeah, whatever. What makes sinusoids special? Many readers with prior familiarity with audio will have intuition grasp of sinusoid as pure tones. It's not clearly stated why sinusoids are so well suited for signal processing and analysis, or where they come from in the first place. The reason underlying the use of sinusoidal waves go mathematically deep, but the basic principles can be understood directly in terms of geometry. Our goal here is to understand the periodicities in signals, and the physical universe readily supplies us with countless examples of periodic phenomena. The rotation of Earth, orbit of Moon around Earth, Earth orbiting the Sun, etc. Each of those phenomena are repetitive. Moreover, each of those phenomena are characterized by a continuous rotation around. Yeah, with a full rotation having completed, the cycle repeats itself. And rotation models repetition. And sinusoids are typically introduced in high school geometry class in study of right triangles. Well, I guess not sinusoid functions, but like just trig, basically. The sine of the angle theta is defined as the ratio of opposite side lengths of the hypotenuse, etc. While it's certainly useful in many contexts, this view can be obscure the integration of sinusoid as waves. Here we use a different but equivalent definition of sine and cosine and angle. First, we will draw a circle with radius 1 centered at the origin. Next, we will draw a line through the origin and make the angle theta the horizontal axis. And sine theta is the height of the point, and cosine is the width. Yeah, when the circle has radius 1, the hypotenuse will always have length 1, so sine cosine measures the height and width. Otherwise, we need to scale the measurement. And by convention, we take theta equal to 0 at this point. Positive angle means counterclockwise, and negative means clockwise. So sine and cosine turn angle into distance. Why does this give us waves? So sine and cosine of a single angle just give us a single number. A single number is not enough to get a wave. But if we change it over time, then we do. Imagine angle varying continuous over time, like the second hand of a clock. We denote it by theta t, and theta 0 at 0 indicates that start position is at here. Equivalently, we can think of this change in theta t in terms of the xy position of the point on the circle at a corresponding angle. To get the wave out this continuous rotation, we can look at what happened to just one of two coordinates at this point, which will be given by sine and cosine over theta. Yes, we can see this rotation kind of trace the sine and cosine functions over time. I guess this kind of thing is pretty easy to understand, but hard to get just internalize yourself with. At least for me, it was really difficult.
This is really important fundamentals for the Fourier transform and stuff like that.
Yeah, exactly. as long as theta keeps moving at constant rates, there will be some minimal time t0 such that theta equal to 0 return to its initial position, the first complete cycle. We will translate this fundamental period into a frequency, measuring the number of cycles completing in 1 second. If we assume theta t is moving at constant speed, then we would have theta is equal to 2 pi over the fundamental frequency times t. So after t equal to t0 second, ft is 1 over t0, so ft times t0 will be 1, and theta t0 will be 2 pi, which will go back into the initial 0 spot. Typically, we don't bother with separate notation for theta t, so instead we just parameterize the x and y positions directly in terms of time and frequency. I like how they give a derivation of where this 2 pi comes from. So every wave, sinusoid wave, that can be expressed with the following standardized form, with the amplitude times cosine of 2 pi and times frequency times t, and plus a phase. So phase is just offset there. So change the amplitude will stretch the wave vertically. I don't know how this graph works, but anyway, change amplitude will stretch vertically. Change in frequency will stretch or compress the wave horizontally. Change the phase will just shift the wave. Oh, okay. So it's three graphs. When changing amplitude, this one gets stretched vertically. This one gets stretched horizontally because it's changed frequency, and the last one got shifted because the phase changes. So every wave can be expressed in the above standard form, but the representation is not unique by using some algebra tricks on trig functions. For example, we can get this because cosine x is equal to cosine x minus cosine x minus pi. So yeah. Most of the time, this ambiguity of representation doesn't cause us too much trouble. It's sometimes useful to know about this, especially via algebraically manipulation wave equations. So properties of waves, symmetry and antisymmetry. So cosine functions has horizontal symmetry. Sine functions are horizontal antisymmetry. Converting between sine and cosine, there are each cosine can be expressed as a sine with the phase offset and vice versa. This rule follows from the fact that all triangles have angles which sum to pi radians. And we are dealing specifically with right triangles. Yeah, it's basically this and this angle and this angle, basically. Average over time. So if we have a wave with some frequency f0 and a fundamental period of t0, if we look at the average value of wave over one period, then it will always come out to be 0. It seems obvious, but worth reasoning through carefully. A careful proof of this statement can be done with calculus. That doesn't sound easy though, but yeah. Anyway, we can reason intuitively via symmetry, like basically for every point will be some opposite point during this interval, so they cancel each other, so we get 0 as the result. Yeah, above argument only work if time interval cover exactly one cycle. Otherwise it doesn't work. So unit and dimensional analysis. So in the previous section we learned about sinusoidal waves which have the standard form like this. In code it looks like this. For many newcomers, this can be difficult to remember. So we can get it easier to understand by thinking about the unit of measurement involved. Once we have each variable with its corresponding units, it's easier to see the right way to. Yeah, I think I heard a lot of people mention dimensional analysis, but that's something that I don't got taught in my high school. Though I probably accidentally, not just like discovered and used it inconsistently personally, but not taught systematically in high school. And yeah, it's actually feel like really helpful technique. Yeah, just basic idea is like we have fundamental properties like amplitude and frequency and phase offset, and each one will have a unit. So time is measured in second, frequency is measured in cycles per second, so inverse of second. 2 pi is measured in radians per cycle. Phase is measured in radians. Yeah, which we can cancel each other. I guess it's interesting because if you let me to do dimensional analysis, I probably will only have second and probably only will have second. And I will treat radians or cycles just as scalar, basically. And I guess this way, this more thorough way of doing dimensional analysis can cover more information, basically. The end result must be in the unit of radians. and phi is also in radians, so it is okay to add the two together. Yeah, if one or the other was not in the unit of radians, we cannot add them directly or interpret the answer as an angle. If we try 2 pi times t divided by f, there we just get wrong stuff. Just dimensional analysis help us to uncover errors. Yeah, by far the most common type of mistake people learning working with signals or just doing all kind of math in general is mismatching quantities. This kind of error can be caught directly by checking units. Yeah, most software don't really help us here. Like, yeah, this kind of code does not have any unit involved. Like in languages like Java or C++, it will not help you either. There are talk about unit libraries in C++, but if it will be 10 times more verbose than stud kernel, then I don't know how many people will actually use it. And yeah, I guess it's always a problem that you can annotate a lot of information statically, but at some point it's just to become so overwhelming that probably will not be beneficial.
Completely agree. It's
Yeah, it's a trade-off.
it's a nice, yeah, it's nice in theory, and it's in some cases necessary, but boy does it make doing computation tedious when you have to go, okay, well, we do this operation and then that operation, but now we have to cast it to get rid of this thing because the library expects this other thing, and
Well, isn't like C++ like committee specifically seems to targeting Rust lifetime says viral annotation blah blah blah. It's like same kind of thing, but I guess I don't want to get into that though.
right,
But
right.
yeah, I guess it's a trade-off that yeah. Yeah.
Do
Anyway.
we want to
Stop
stop here
here?
for now?
Yeah,
I'm just thinking
sure.
we have, depending on how long the audio and signals are, and then we can, the exercises might be actually worth going through, but they might be, I, yeah.
This exercise is just a bunch of algebra stuff, so yeah, I don't know.
Yeah, never mind.
Yeah,
Oh.
maybe let's just stop here.
Okay.
And I guess we can just skip the audio stuff. People can read it on their own. Doesn't seems it's more like an example. It seems.
Oh yeah, it seems more like like what we as humans experience, and the physics, not the signals.
Yeah.